Sauce, Kevin here, and you have a dilemma. I have 2 envelopes and you can only choose one. There's door number 1 and there's door number 2. There's actually 3 envelopes here. Great. Now we no longer have a dilemma. Here's why. Di comes from the Greek twice, and lemma means premise. So a dilemma involves 2 premises from which you have to choose. Adding a 3rd envelope means that this choice isn't technically a dilemma. But it does set up a very famous paradox. Wait, let's dissect the word paradox like we just did with dilemma to find out exactly what a paradox is. Okay, para comes from the Greek distinct from, and dox comes from doxa, meaning our opinion. Paradox translates literally as distinct from our opinion. So there you go. Now, distinct from our opinion? That didn't really help at all. I thought a paradox was like an unsolvable brain teaser. So how do 3 envelopes set up a paradox? What is a paradox? In 1961, logician and philosopher Willard Van Orman Quine outlined the 3 categories of paradoxes, and I have them each hidden inside these 3 envelopes. 1 represents the kind of paradox that you're most familiar with, those that defy logic, like the impossible waterfall from this video's intro. The other 2 are what? Well, let's crack one of them open and find out. Falsitical. This is why Achilles can never catch a tortoise. We'll use this bootleg Rambo to represent Achilles, and a Ninja Turtle Pez will be our tortoise. If the tortoise gets a 100-meter head start, then Achilles starts running. By the time he gets to the 100-meter mark, the tortoise will have moved another meter. It takes Achilles some more time to get to that 101-meter mark, and in that time, the tortoise has moved even further. Achilles will always be catching up to the place where the tortoise was as the tortoise inches forward. The gap gets smaller and smaller, but the tortoise is always slightly ahead. According to Greek philosopher Zeno of Elea, who dreamed up this paradox 2,500 years ago, the fastest runner in the world can never overtake a tortoise in a race because you can infinitely divide the distance between them as the tortoise advances. But that's ridiculous. We know it's not true. Even with a head start, I could outrun a tortoise, and I'm no Achilles. So how can this be a paradox? Zeno knew Achilles could catch up to the tortoise in real life, but he couldn't prove it mathematically. He thought there would be an infinite number of new points for the tortoise to reach that Achilles had to reach because he didn't know that an infinite series of numbers could add up to a finite value. No one knew that for another 2,000 years. What we now call a convergent series, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 goes on forever, but it eventually adds up to 1. And at that 1 is where, mathematically, Achilles finally reaches the tortoise. We knew that Achilles could catch up to the tortoise, but it took inventing calculus for us to prove why. Which is why this paradox that confounded great minds for thousands of years is falsitical, described by Quine like this. A falsitical paradox packs a surprise, but it is seen as a false alarm when we solve the underlying fallacy. Okay, that's 1 paradox envelope down and 2 to go. And behind number 2, we have veridical. For this, we need a game show. Okay, I'm gonna replace the 2 envelopes we've already opened with some prizes. How about $1 million will go into one of them, and the Glob Glow Gab Galab will go in the other. It's a good enough prize as any. The third envelope still contains the term for the final type of paradox, which we'll get to later. All right, I will shuffle these up so you don't know which is which. Now you've got 3 envelopes, X, Y, and Z. Pick the correct one and you win the grand prize. After you make your selection, let's say envelope X, the game show host reveals what's inside one of the 2 remaining envelopes. It's the glob. Now there are only 2 envelopes left, the one that you chose and the remaining mystery envelope. He gives you the option to switch your envelope. Should you do it? Does it even matter? I mean, at this point your odds of winning are just 50-50, right? No. You should always switch, and here's why. The odds of winning with your first chosen envelope are 1 in 3, so you have a 33.33 repeating chance of being right, and a 66.66 repeating chance of being wrong. When the game show host revealed the glob, it didn't suddenly improve your odds to 50-50. The proof is in the options. After first choosing an envelope, the thing revealed by the host will never be the money because, well, that would ruin the tension of the game show. So if your initial 1 out of 3 pick wasn't the money, and the money is Y, then the host will reveal Z. If you chose wrong and the money is Z, the host reveals Y. If you luckily chose the money the first time, then the host can reveal either Z or Y. It doesn't matter. No matter what, you're still stuck in that initial 33% chance that you chose right the very first time. But if you switch, regardless of the prize revealed, you now leap into the 66% zone. You've doubled your chances of getting the money. To put it another way, when you're asked if you want to switch, you're actually being given a dilemma. Do you want to keep your single envelope, or do you want both of the other 2? It just so happens that you already know what's inside one of them, but since the one revealed will never contain the money, the chances that the other unopened one has the money are twice as high as the first one that you chose. The Monty Hall problem blew up after a 1990 Parade magazine columnist advocated switching doors in the same scenario from the game show Let's Make a Deal. When she told readers they should always switch to improve their odds of winning, nearly 1,000 people with PhDs wrote in to tell her that she was wrong. She wasn't wrong. They were. So the Monty Hall paradox, like the potato paradox we recently covered, is an example of one that is a veridical paradox. One that initially seems wrong, but is proven to be true. Quine said, a veridical paradox packs a surprise, but the surprise quickly dissipates itself as we ponder the proof. Okay, there are paradoxes that seem absurd but have a perfectly good explanation, and ones that seem false and actually are false because of an underlying fallacy, even if it takes a major advance in math to prove it. This last envelope contains the kind that we think of when we all think of paradoxes. Antinomy, the grandfather paradox, where you go back in time to kill your grandfather when he was a child, but that means your father was never born, so you were never born, so how could you go back in time to kill your grandfather? It's ridiculous. Metaphysics proposed a solution to this, but these types of paradoxes are not true or false. Actually, they can't be true and they can't be false. As Quine put it, they create a crisis in thought. I am lying. If I'm lying when I say that, then I must actually be telling the truth. But how can I be telling the truth if I'm lying? The liar's paradox is an example of antinomy, which literally means against laws, and highlights a serious logical incompatibility. Quine said, that this tape thing was a good idea in theory, but in practice, not so much. Quine said, an antinomy packs a surprise that can be accommodated by nothing less than a repudiation of part of our conceptual heritage. Here's the thing. Antinomies are paradoxes to us all. Falsitical and veridical paradoxes are only paradoxes to those who don't know the solution, but they still have value. Every time we resolve a scenario that runs counter to our or someone else's initial expectations, every time we learn the how and the why and share that information, we're refining and clarifying knowledge, which makes all three types of paradoxes excellent tools for reasoning. Whether or not something is paradoxical to an individual depends on the accuracy of their expectations. Today, modern mathematics has given us the ability to show that Zeno's paradoxes are falsitical. But they were pure antinomy, unresolved to everyone for millennia. Quine himself said one man's antinomy is another man's falsitical paradox, give or take a couple of thousand years. Who knows which antinomies of today will be solved in the future? Right now, we struggle with the paradox of the faint young sun. Our current knowledge of stars says that billions of years ago, our sun wasn't hot enough to keep the Earth from being a ball of ice. But our geological evidence shows an ancient Earth with liquid oceans and budding life, when everything should have been frozen. How could the Earth have liquid water without a sun hot enough to melt ice? It's antinomy until we fully comprehend the situation. Maybe our current understanding of the sun isn't perfect, or maybe our knowledge of early Earth is missing some pieces. A paradox is a problem where the solution is or is made to seem impossible. Sometimes they're purposefully designed for fun because our minds like puzzles. Sometimes we just stumble on a gap between what we know and how we talk about what we know, and what is actually true. When we solve an impossible antinomy, it becomes falsitical or veridical. Someone who knows the answer can see what the problem was all along. We tricked ourselves by knowing too little or by asking the wrong question. In one way or another, all paradoxes come from people. By challenging us to find the flaw or fill the gap in our knowledge, paradoxes help us define and push our intellectual boundaries. There's always more for us to know, whether we know it or not. And as always, thanks for watching.